What's happening if the velocity is staying
MGH.
constant? Only mgh? What energy is being converted to mgh if this is the forward force and the distance covered is a kinetic? Is there any change in
Kinetic
kinetic
energy?
energy? Is there any change in kinetic energy? Initial final velocity,
No.
there is no
Because
change.
velocity is constant.
Yeah, so change in kinetic energy is zero, right? What about gravitational potential energy? Is there a gain in height?
That increases.
Yes, and
Yes.
that's equal to what? Mgh, right? And then after this, what else can we create an equation? Can we make an equation in terms of energy conversions? If this is the mg and this is the theta. Now tell me, what's the total work done by the engine of this cart? If F is a forward force and S is the
Force
distance to the
into
cover.
force into S.
Force into displacement, okay. And
S.
okay, F into S. And what will it get converted to? How many forms of energies?
Work. Oh wait. It's work done. So
Yeah, it is well done, but it is
power.
converted to other forms of energies as well, right? It is converted to gravitational potential energy. Is it converted to kinetic energy?
Yes.
Is it? There is no change in kinetic energy. How will it be converted to kinetic?
No.
Yeah, no change in gravitational kinetic energy. Only it is converted to mgh. And is there any other form of energy that it is converted to? Do you remember something from the inclined plane? Anything? And
Therm.
frictional forces are zero. Now, do you remember something from the
Thermal.
inclined plane? Thermal? I said frictional forces are zero. How could thermal energy exist?
Okay.
And if frictional forces are zero, then thermal energy has to be zero. Okay, no conversions into thermal.
Yeah.
Then what else? Is there any other resistive force acting on this cart? Is there any other force acting down this plane on the back side? You remember any force in this
The
direction?
horizontal component.
Yeah, what's its value?
F sine theta.
Yes, F sine theta. This F sine theta, since it's in the opposite direction, it will act as a resistive force. So work is done against this resistive force. Instead of F, I'm writing mg, okay? Not F, it's mg. It's the weight, mg sine of theta. F is that forward force, the total force. It's a weight, okay, mg sine of theta. This is the force, but when you multiply it with displacement, it becomes work. But this component is actually work done against resistive force. There. So these are the energy conversions in this equation, in this situation over here. You get this?
Okay.
To tell me what to do. Okay, first of all, this
Hey,
is
can you
the,
scroll up? Can you scroll up?
yes. Take a screenshot of this or a picture of this
Yeah.
so that we can save time.
Yeah.
Let me know
Can you
when it's
scroll
done.
up? Yeah. Okay, it's done.
Okay. Now, if this is an inclined plane, this is an angle theta, and there is an object sitting right over here. Okay, that's too steep. Let me make it a bit flat. Okay, this is an inclined plane, and there is an object right over here. Now tell me all the different forces that act on this object.
Okay, there's force backwards.
Backwards, meaning
There's
down
a
the plane.
horizontal component.
Okay,
Yes,
you
down
have
the plane.
you have to call it down the plane. Okay. So and what's its value?
Okay. Mg sine theta.
Yep, it's mg sine of theta. And what else is there?
There's a forward force, the thrust
Forward,
of the plane.
meaning perpendicular to the plane or in that direction.
The, yeah, that direction.
This
Parallel.
one, this one or that one?
No, not perpendicular. The
Okay,
right one.
not perpendicular, the right one. What force is this?
That's a net force.
Well, the object is just
Wait, no, sorry, it's not the force, it's like the thrust.
listen. The object is just sitting over here. It's not moving. So there's going to be no force in the forward direction. Okay?
It's
Yeah.
going to be a perpendicular force that's going to be the normal reaction.
Yes, the normal reaction force will always and always exist. What else will be there?
Perpendicular to the plane.
Yeah, it's perpendicular.
Downwards, opposite the normal reaction would be the vertical component, mg cos theta.
Okay, it's mg cos of theta acting opposite to the normal reaction force. But aren't you forgetting another
and then
force?
Weight acting downwards.
Yes.
Weight acting downwards.
Weight is acting downwards, correct. This is your mg. All right, so these are almost all the forces when an object is stationary. Now, if this object was moving and there was a forward force produced by the engine, then that would have been in that direction, okay? And if there were some other frictional forces, this plane was rough, then what other force would exist if the plane was rough?
Resistance.
Frictional force, right? Yeah, the resistive, but what sort? It's frictional. And its direction is always opposite to the direction of motion. You should know all of these forces, okay, by heart for an inclined
Also, what
plane.
do we exactly call the forward force?
What do we call the forward force? This one?
Yes.
This is called the forward force of the engine. It's not the thrust. Yeah, it can be called the thrust as well. Yeah, the thrust of the engine. Okay.
Also, what if we call it the net force?
What do we call the net force? Or the N?
Yep.
The net force is a resultant force. It's called the resultant. What else do we call it?
Yeah, but what if we call that forward force resultant? Would it be fine?
No, it won't be fine because that's not the resultant force. That's the total force acting forward. The total force, the net force would be the forward minus the backward. Okay?
Right. Okay.
This F net force is the force which you apply in Newton's second law, and this is achieved when you subtract the backward forces from the forward force. The forward force is F, subtract the backward forces which are F and mg sine of theta in this case.
Yep.
Clear? Now, so
Clear.
this was about the inclined plane. After this, we did momentum as well in the last class, if you remember. So if I have two bodies
Yep.
moving towards one another, this is the mass m1, this is the mass m2, moving with a velocity v1, which has a value of, let's say, 2 meters per second. And this one was moving with a speed of, let's say, 3 meters per second. After collision, the mass m1 moved in the opposite direction, the speed of 1 meters per second. This other mass moved in the other direction with a speed of, let's say, 1.5 meters per second. This is the M2 has a value of, let's say, 2 kg, M1 1 kg. This is 1 kg, this is 2 kg. Now if I were to ask you, okay, let's assume we don't know this velocity. Now if I were to ask you to calculate the direction and the value of this velocity, how to do that?
Using the conservation law.
What is it called? Yeah, the conservation
of energy.
Not energy.
Of energy.
Not
in
energy.
A closed.
It's not called conservation of energy. Did we do any new quantity? You remember this? What was the P?
P. Yep. Moment.
Momentum. Remember the momentum?
Yeah.
What's the formula for momentum?
Isn't it also like conservation? M1 into U1 minus M2 into U2. Wait, oh,
Yeah, so let's just make the equation. So it's m1, let's say it's 1 into the initial velocity, which is u, plus what else? 2 into, this is going to be plus 3 or minus 3?
-3.
Okay. And this is going to equal, okay, this 1 kg mass is moving at a speed of 1 meters per second. Is this positive or negative, the one? Given the direction, it's to
Negative.
the left, it's negative. Yeah, because it's the same direction as 3. So it's going to be 1 into minus 1. And now I need to find this velocity of 2 kg, 2 into v. I'll just solve it and you get the answer. 2 minus 6 equals minus 1 plus 2v. And this is going to be minus 4 plus 1 upon 2, which is equals to v, which is equal to minus 3 upon 2, and then minus 1.5. And the minus 1.5 means that this mass will not go to the right, but rather it will also go to the left, because minus is the direction that we've considered the left side. And that's
Right.
the speed, 1.5 meters per second. Now you were asking about energy. Energy is only possible if this was an elastic collision. The law of conservation of energy, is always going to be applicable. But in this case, since this is an inelastic collision, there will be some energy lost as heat that we don't know. And we won't be able to use it
Right.
in our calculations. But in case of elastic collisions, we know that there is no loss of energy. There is no energy loss, and in this case, we can use the total energy before and after collision is equal. But in case of inelastic collisions, we cannot use the law of conservation of energy because we don't know the heat which is produced. But law of conservation of momentum is always applicable. Okay.
Okay.
Yes. You were asking something?
Nope.
Okay. So you may take a screenshot of this, I guess, and I can move on.
Yep.
After this, we can move on to the. Okay, so this was a quick recap of what we did. Okay, do you remember what power is? The definition of
Just
power.
work done over time.
Okay, work done per unit time. That's the equation. But if I were to ask you to write down the definition, it's going to be rate of flow of energy is called power. Rate of flow of energy, or you could also say that the work done per unit time is also power. Okay, so this was power. What's the unit of power?
Watts.
Watts. Or we can also call it joules per second. This is also a unit of power. Joules because joules is energy, and seconds because time is beneath in the denominator. All right, after this, oops. Okay, after this, we've got what's called, we did power. Yeah, I told you if you know the concept of homogeneity of an equation, and you said you needed some to review that, so let's do that. Okay, what is a homogeneous equation? Any idea?
Equations that are equal.
Equations that are equal.
Homo means same, so
Homo means same, and equation means yes, we are dealing with an equation. Homogeneous actually means same, but it's not the equations which are equal, it's actually the base units of each component in that equation are equal. It's an equation in which the base units of every component are equal. Every component are equal. Okay, so how do we identify the component in an equation? For example, the inclined plane example that we did up there, I told you that the force multiplied by the displacement is equal to the change in gravitational potential energy plus the work done against resistive forces, mg sine of theta into the displacement. And if there was change in kinetic, if there was change in velocity, then there would have been change in kinetic energy as well. Component of an equation is basically that part of the equation which is separated by a plus or a minus sign in the equation. Okay. So these, how many components do we have in this equation?
4.
4 components, correct. Now, if we were to break them down into their base units, do you know what base units are?
Yes.
What are they? How many base units are there
Mm,
in total in physics? 7 base units.
7. 7. Yep.
Yeah. Can you name them?
Time, mass.
Time is a base
Uh,
unit, or is it a physical fundamental quantity?
okay, that's the fundamental quantities.
So, what's the unit of time?
Second,
Yeah, okay. Next.
meter, meters.
Okay, next. Kelvin?
Meter, joules.
Joules? Energy? No, 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 no. Energy is not a fundamental quantity. Kelvin, temperature, remember?
Yes.
And what else? Kg, mass,
Okay, mass. Yep.
and what else? There's N,
Amperes. A. I.
ampere,
I'm sorry. Yeah.
am,
A.
the ampere. So we've got 5, 2 more. The 2 are very less commonly
V.
asked. The
V.
CD and the mole.
Watts. Volts. Wait, watts.
Volts are not base units, they are derived units. These
Okay.
are the only base units that are out there. 1, 2, 3, 4, 5, 6, 7. Bus, that's it. No other. All other base units that we are dealing with are derived units. They are not base units, okay?
Okay.
Volts is a derived unit. CD, do you know what CD is?
Um. No.
Candela.
Okay.
It's for the
I've come
intensity of
across
light.
in the charts.
Yeah, the luminous intensity. And moles, that's also done in chemistry. Mole is a unit of amount of substance which is measured. Okay, but these two are not commonly used in physics. In physics, we only deal with these 5 base units that we have. And most 99% uh, of the calculations are done using these base units. Okay. Now
Okay.
let's move on to breaking these equations into the base units. Force and distance. Can we break them down? Uh,
Yes, we can.
okay, so tell me, what are gonna they be?
M.
M. Okay, M is mass. What's the base unit of mass?
Kg.
Okay, multiplied by
Kg.
what else?
Seconds. Oh wait, sorry. Meters.
What else? Is that all? Okay, now let me correct you. Basically, kg is not a unit of force. The unit of force is Newton. Kg is a unit of mass.
Okay.
Can we break down the Newton into these base units? What is force equal to? Force is equal to mass into acceleration.
Yep.
What's the unit of mass is kg?
Kg.
What's the unit of acceleration?
Ms minus 2.
Yeah, so this force is actually kg ms minus 2. So this is kg ms minus 2.
Right.
And this kg ms minus 2 is being multiplied with distance, right? Which is the meter. Now if you multiply them, what will you get?
We get
Kg will stay as it is. The meter gets multiplied with the meter. It becomes meter squared
right.
and s minus 2. This is the base unit of force into distance, okay? Base unit of force into distance is kg m squared s minus 2. Or in other words, I could say this is the base unit of energy. Can I say that? Because work done, force into distance is work done, right?
Yep.
and work done is energy. So this is the base unit of energy. If this is the energy, are each of these energies as well? mgh, is it a form of energy? Are each of the other components
Yes.
in the equation energies? mgh is a form of gravitational potential energy. mg sine theta into distance, is that also a form of energy? Is it work done against the resistive forces?
Yes.
Yes, of course, yes. Because it's force, mg sine of theta is a force, s is a distance. So when force into distance means energy.
Oh, work done. Okay, right.
Yeah, work done against resistive forces. And what about this? This is also an energy,
Yes.
right? So each of these components must also have the same base units as kgm squared s minus 2 as F into S, because these are also energies. Such an equation in which all the components have the same base units is called a homogeneous equation. Okay, this is a homogeneous equation. Now let's verify this. Let's find out the base units of each one of them. What's the base unit of MGH gonna be? It's easy. MGH.
K- kg.
Kg.
Do we include 9.81?
No.
ms square. Okay, ms minus 2
What else?
and s.
S
Oh,
of
sorry,
M.
sorry. Meters.
Yep, meters. So you get kg m squared s
S
minus.
minus 2.
Is it the same as the one which we got over here?
Yep.
Okay, so the first component is verified. That's correct. Now the second component, mg sine of theta into distance. Now let me tell you something. Sine of any angle, cos of any angle, these are ratios, trigonometric ratios, and they have no units, okay? Just have to ignore them. Mg sine of theta into distance. You need to find out its base unit now. Come on, help me out.
Okay, kg ms minus 2.
Ignore the sine
Um.
theta.
Okay, so we ignore it.
Yes, of course, I just told you right over here, because it has no units. It's a ratio.
Okay.
Cos theta also has no units, so you have to ignore the cos theta as well, if it came anyway.
Into into meters. That gives you kg ms square. Kg m square s minus 2.
Yep, it's the same as the ones which we've got before this. It's
Ah.
kg m squared s minus 2. And then we've got the next component of the equation, which is kinetic energy. What's the formula for kinetic energy? Half mv squared.
Yep.
So how to find out the base units of half mv squared? Half again is a number, right? This is a number. It has no units. No units.
Right.
What's the unit of mass?
kg m
It's a unit of.
ms minus 1. Ms minus 1 squared.
So what will it become?
M square s minus 2.
So all of these components have exactly the same base units. kgm squared minus s minus 2. Okay, same base units means that this equation is correct mathematically, and it's a homogeneous equation. By the way, remember one thing: for any equation to
Wait,
be
can I take a
mathematically,
picture?
yeah, sure, you can take a picture.
Okay.
For any equation to be mathematically correct, it has to be a homogeneous equation, okay, in physics. Remember that. All the equations that we did in physics are homogeneous equations. If they are not homogeneous, then the equation is not correct, okay? State that point somewhere. Let's do
Can
one
you
more
give an
example.
equation so I can figure it out?
Yeah, I'm doing that. You can take all the equations of motions and find them out. S is equals to ut plus half at squared. Do you remember this equation?
Yep. Equation of motion.
Yeah, any equation of motion can be used for practice. You can use v squared equals u squared plus 2as as well. You can use any one of them. But before I move on to any other equation, let's try this one first. Okay, so what's
So
s?
m
M.
sorry, yeah, m
So this
into
means
equal to
that each component would have a unit of
m
m, right? How many components are there in this equation?
2.
Two or three? Isn't s the
Okay, including s3.
yeah, three components. Okay. So now let's go on to this one. What's the u?
ms minus 1 into s
What will this become?
ms square minus 2.
No, they'll cancel each other out. It's s minus 1 multiplied by the s.
Okay, right, that would be 0.
1 minus 1 becomes s to the power of 0, which is equal to 1,
1.
right? So it's m. And then this last one. What to do?
ms minus 2
Yeah.
into s square.
Now what would happen?
That would cancel out.
And I'll be left with the meter.
Okay.
Yeah.
Wait, ms minus 1 squared.
The whole thing squared, okay?
Yes.
So what will this become?
M squared and s minus 2.
Yes.
Oh, 2 minus.
They'll get multiplied, yeah. Will become minus 2. Okay, whenever you have brackets, they'll multiply each other. What about this one? It's u squared.
ms minus 1 squared. So that would be m squared s minus 2.
Same thing, right? What about
Yes.
this one?
2 into ms minus 2 into.
Do you need the 2?
Oh, no, no, you, oh, no, 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 no.
Then what to do?
ms minus 2 into s into meters. M squared s minus 2.
Okay,
Okay.
same. So you could do the same thing for each and every equation of motion that you have. Okay, so that's one of your homeworks. Try finding the homogeneity of each of the remaining three equations. So wait, remaining two equations of motions actually. What are the two? V is equals to u plus et and s is equals to v plus u upon 2 times t.
Into t.
Okay, these are two equations that you need to figure out the homogeneity yourself. I guess that's more than enough for homogeneous equations. Do you
Yep.
want me to talk more on it or should I move on?
No, no, move on.
Okay, I'll move on then. Okay, efficiency. You need to calculate efficiency. Efficiency is just the ratio of the useful stuff divided by the total stuff times 100. Now, if you're talking in terms of power, efficiency is going to be the useful power output, useful power out divided by the total power input
Input.
multiplied by 100. If it's in terms of energy, then it's going to be useful energy divided by the total energy times 100. So what is efficiency? Efficiency is the ratio of the useful power to the total power, or it is a ratio of the useful work done to the total work done, or it is a measure of how efficient something can be performed, or uh, how something can be performed without wasting something, without wasting a quantity. Now in our syllabus, since we are concerned with power, You are defining it in terms of power and energy as well. The definition, if you're asked the definition of efficiency, you don't need to write down the wording. You could just write down this equation. Useful energy output, energy or power, okay? Okay, let me write the power stuff differently, separately. Useful energy out divided by the total energy in multiplied by 100. By the way, even if you don't multiply it by 100, it's still gonna be efficiency, okay? Even this ratio is efficiency. If you multiply by 100, that means you are just converting it into percentage. If you're not multiplying by it by 100, and that means you are just getting an answer in terms of fraction or in terms of decimal, okay? And by the way, efficiency
Okay.
is usually never 100. Okay, most of the time the efficiency is never 100. But there is one case in which it can become 100. And that is in case of an electrical heater. In case of an heater, the efficiency can become 100% as well. Why? Any idea?
Because it is heat.
Yeah, so what?
Heat is what is needed.
Heat is what is needed for what?
So it gets
For the heating. Yeah, so no energy is wasted actually.
we
All of
get
it.
rid of it.
All of it is used up.
Yep.
Basically, efficiency, what decreases the efficiency is usually the frictional forces of the system or the resistive forces of the system that waste the energy in form of heat. But if heat is the energy that you need, then there will be no loss of energy. All of it would be converted into heat, and therefore it can become approximately 100% as well. This was actually a very famous MCQ in CIEs, okay? It has been repeated several times. Even in my attempt it came, although it was an MCQ of the past papers, okay? That electrical, choose the correct statement, and one of the four statement was that electrical heater can have an efficiency of 100%. Assume for you. Okay, so if you have some, let's say there is some appliance over here.
Wait, there was a question that was really hard. Wait, I'll send it to you later.
If you want, you can send it to me right now. We can try it. If you have it on WhatsApp.
I don't know where it is now.
Okay, you can send it to me later on. But if you have some energy, the total energy that you provide is 100 joules, but the output useful energy that you use is 80 joules, and the efficiency is just simply going to be 80 upon 100, 80% basically, when you multiply this by 100
Right.
as well. Okay, so not much difficult. Okay, it depends. If the examiner doesn't give you a difficult question, it won't be that difficult to solve, okay? And after the efficiency, we've got, okay, we've reached to to section 1.4 of unit 1. And now let's do this, materials. Okay, so density, what's density? Density by definition is the mass per unit volume. So mass divided by volume. The unit of mass is kg, the unit of volume is
kg.
meter cube. What's going to be the unit of density? Kg, m
kg
minus c, right? When you take the denominator to the numerator, the power becomes opposite.
Negative.
Gains a negative sign or a positive sign if it was negative in the denominator. Understand upthrust fluid friction? Okay.
Yes.
Weight of fluid displaced. Yeah, now we need to look at the upthrust force. Okay, what is upthrust force? Upthrust.
With fluid dynamics?
Fluid dynamics has started, yes. This comes under materials. Now, so what is upthrust force? Upthrust force is basically a force which exists in fluids due to difference in densities. Difference in densities. Now, if I have an object, I have a container, and in this container, I have a fluid. Okay, And at this, where I immerse an object at this some level in this fluid. At the base of this fluid, sorry, at the base of this object, right over here, which is at a depth of, let's say, h height, sorry, the depth of this base is h, this object will experience a pressure force. Okay, it will experience some pressure at this particular point. The formula for calculation of pressure in fluids is rho gh. You remember this formula?
Yep.
Rho represents, what does rho represent?
Density.
Density of what? The object or the fluid?
Oh, fluid.
Yes, correct. G is the same, 9.81, and H represents the depth. But if you look at the height, at
I
the,
don't understand why it's called rho.
you don't understand why it's called rho? Why is this called rho?
Yes.
Because this is not English. It's from Latin. It's a Latin alphabet.
Oh.
Oh, you didn't even know this. All right, nice, nice. You are an interesting person. That's great. Okay, so you didn't know why this is called omega, or why this is called rho, or why?
I know alpha and beta and.
Yeah, the alpha and the beta. Well, they are very pretty obvious. Alpha, beta, gamma. You didn't know why each of them are called
Yeah,
these.
I knew the gamma ones too, but I didn't know this one.
Okay, okay. All right, all right. So remember,
No
whenever.
one told me.
Okay, okay, nice, nice, nice. Okay, I did tell you now. Okay, so give me credit for that. Just kidding. Okay.
Yeah.
Now, if you look at the base, sorry, look at the top of this object. This top is at a relatively smaller depth as compared to the base. The base is at a depth of h, but the top is at a depth of, let's say, h upon 5, right? Just assuming this, where h upon 5 is actually less than h, okay? You know that, right? Because this is a fraction, this is the whole number. Is this clear?
Right.
So now, if you look at this equation over here, there is a direct relationship with the depth and the pressure. So basically, at the greater depth, meaning at the base, the pressure due to this fluid is going to be greater than the pressure on top of this object. Okay, the pressure on top by the fluid is going to be smaller than the pressure on the bottom by the fluid on this object, due to which from the greater fluid side to the lesser fluid side, a force will act on this object from the greater to the lesser fluid side due to the difference in pressures. This force that acts is called the upthrust force. So what is upthrust?
Yes.
Upthrust is the force that exists in fluids due to difference in pressure. Fluids due to difference in
Different
pressure. Okay, at different depths, of course. There is a derivation, a small derivation of upthrust that you must know. Okay, and now let's look at that derivation. Now, for instance, and that's pretty easy. So now this is an object that you have, and there is its top and its bottom, meaning its base and its roof. Now this object is placed inside a fluid of a constant density. This object itself has some mass. Sorry, it has some volume. Well, now let's assume this is the object and this is the base, and okay, this is a cubical object placed inside a large container.
Okay, wait, sir, 1 second. Okay.
Yeah. Okay. So now basically this object is placed inside a container with a fluid. Okay. The fluid is of constant density, rho. Okay. This is the density of that fluid. The gravitational field strength is G. Now, basically, the the depth of the base of this object is h1 and the depth of this top of this object is h2. Let's assume that. Now we need to derive an equation for the upthrust on this object due to the fluid in which it is immersed. So now what we are going to do is, I told you that upthrust is a force that exists due to difference in pressure, right? So basically, what's the formula for pressure, the general definition of pressure? Pressure is force per unit area. Is that true? Okay, so I was saying that the definition of pressure is force per unit area, right?
Yes.
And the upthrust, if I call this force upthrust, then I would have to call this pressure change in pressure, the difference in pressure, right? Because upthrust is the force that exists due to change in pressure, a difference in pressure at different depths in the fluid. Is that true? The
Yes.
definition of upthrust, this was a definition, okay. Upthrust is the force that exists due to difference in pressures. So if I want to calculate the value for upthrust, it's gonna be the change in pressure. If this is the upthrust, this is gonna be the change in pressure. Okay, how to calculate the change in pressure? So basically, to calculate the change in pressure is actually equal to the pressure at the base minus the pressure at the top. The pressure at the base in fluids, the pressure due to fluids is rho gh, right? Rho g at the base is gonna be h1 minus the pressure on top is gonna be rho g h2. Can I take rho and g common from here?
No.
I can.
I mean, by subtracting the height.
Oh, I can take rho and g common outside the brackets and I can leave h1 and h2 inside the brackets. You remember this from math?
Yeah.
You don't?
No, I.
Okay. So now basically we got the change in pressure in these terms. You know that density is mass upon volume, right? Density is mass upon volume. So I can replace the density by writing, okay, wait, before replacing the density, okay, I'm not replacing the density, sorry. Not replacing the density. Now I'm gonna use this equation and instead of this change in pressure, I'm gonna write upthrust divided by the area, okay? Instead of the change in pressure, I'm gonna write upthrust divided by the area because change in pressure is the upthrust divided by the area. Upthrust divided by the area of that object. Area is actually the cross-sectional area on which the upthrust is acting. Basically, this cross-sectional area on which the upthrust force is acting. This area and the base, say this area. These are the two surfaces on which the upthrust force is acting, right? So these are the two surfaces which are at different pressures. Now, if you got this, you have the rho, you have the g, you have the h1 minus h2. h1 minus h2 is actually the length of the object. If you multiply it by the area, you'll get the equation for upthrust. Multiply both the sides by this area, so area on the left will get cancelled out and area on the right is right over here. Now area into change in height, h2 minus h1, this h2 minus h1 is actually the side length, is the length of one side, right? And when you multiply that by the base area, you get the volume of this object. So the g stays constant, the rho stays constant, but instead of the h1 minus h2, which is actually the length and area, when they multiply, you get the volume. This is the volume of this object in which is immersed. This rho is actually the density of the fluid in which the object is immersed, and Fu represents the formula for upthrust. This is the formula for a calculation of upthrust. So if you need to calculate the upthrust from any body placed in any fluid, use the formula rho Vg. But remember, rho and V are of different objects. The V is for the fluids and V is for the object and rho is for the fluid. This was the entire derivation. Now what did I do over here?
You derived the formula?
Basically, I wrote a formula for in terms of pressure, right? So this is a definition of pressure. Pressure is equal to the force per unit area. And if it's the upthrust force that I'm dealing with, then it's going to be a change in pressure because upthrust is due to the change in pressure. difference in pressure. Get it?
Yep.
Then what about this thing? What did I do over here?
Um, Try to derive the formula for the rho GH.
What's the first equation?
The pressure, the difference between the pressure, the difference of pressures
In between what
between
points?
H1 and H2.
Okay.
Sorry, like the
The
top
base and
surface
the
and the
top.
base.
Okay, okay, great. And so the pressure in fluids becomes rho GH1 minus rho GH2. Then I took rho G common. After taking rho G common, I know the change in pressure can also be written as upthrust divided by the surface area, meaning the cross-sectional area of this object on which the upthrust is acting. So the cross-sectional area is then uh, multiplied on both the sides. The equation on both the sides is being multiplied by the cross-sectional area to make the upthrust the subject. And then when the cross-sectional area goes over there, you know that cross-sectional area multiplied by the side of an object or the length of the object will give you the volume of that object. So you get an equation of upthrust in terms of the density, in terms of the gravitational field strength, and the volume of the object. Rho Vg becomes the formula for upthrust, where rho represents the density of what? Right? And V represents the density of what? The volume of object. G represents 9.81, the gravitational field strength. Thrust equation. Okay, so now if you have an object of volume 110 meter cube immersed in water of density 1000 kgs per meter cube, and if I were to ask you to calculate the upthrust force that is applied on that particular object of this volume. Okay, and now let me tell you something very, very special over here. This volume that I've calculated, this volume is actually the volume of the object which is immersed, okay? The volume of object immersed in fluid. Since in this case the entire object was immersed inside the fluid, I can take rho Vg and I could place the volume of the entire object in this equation to get the upthrust force, okay? This is important. What is V? V is the volume of the object which is immersed.
Okay.
Okay, if half of the object was immersed, then I would take half the volume of that object over here, okay? Now, after this has been dealt with, now if I gave you uh, these two values and I asked you to calculate the upthrust force, you just simply use the formula G, plug in the value of rho, and G is that what it was, and you get a force in terms of Newton for the upthrust. Get it? This is how you calculate the upthrust of an object placed inside a fluid. Okay, so before we move on to Stokes' law, let me define what viscosity is. What is viscosity? Viscosity is also called fluid friction. It is the resistance of flow, or yeah, resistance to flow of a fluid. And it has a direct relationship with the density of the object. So the greater the
Yep.
density, the greater the viscosity,
More
and
viscous. More viscous.
more viscous that object is, and the harder it is for it to flow. Harder it is to flow. And by the way, the high viscosity of water is highly viscous. Basically, it
Yep.
is more viscous compared to hydrogen sulfide or compared to other elements which are similar, which have a similar mass as water. Reason for that is hydrogen bonding in water. Hydrogen bonding makes water very viscous. It increases the fluid friction. It increases Hydrogen bonding causes the molecules to stick to one another and prevents them from flowing. Okay, so it's the hydrogen bonding that causes the viscosity of water to increase. And this is just a bit of a chemistry touch. Now moving on to the real physics topic. You have an object, actually not an object, let's assume there is some oil droplet. An oil droplet. And this oil droplet enters a big tub filled with water to a certain height, certain level. As soon as the soil droplet enters the tub, starts going downward. As it starts going downward, uh, initially no force or no resistive force is experienced by the oil droplet before it entered. Because let's assume that outside the fluid, the entire space is vacuum. But as soon as this oil droplet enters this fluid, experiences a variety of forces. Now, can you name a few of these? Can you name those forces? The first force is, of course, going to be the weight of that oil droplet. What else will it experience?
Upstairs,
It will experience upthrust force, and what
drag,
else?
drag.
Viscous drag force. Viscous drag. This is due to the viscosity of that the fluid. Viscosity of fluid. And this is the upthrust due to difference in densities. And this is more marked in liquids as compared to gases, okay? And this is the weight. So now a time will come, initially the value of upthrust, viscosity, these initially the resistive forces are going to be very small, but as soon as this object reaches its gain speed, as soon as this oil droplet gains speed, these forces, the resistive forces will also increase in magnitude. As these resistive forces increase in magnitude, a time will come when the resistive forces will balance out the weight of this oil droplet. Right? The upthrust force plus the viscous drag would become equal to the weight. Upthrust and the viscous drag force, let me call it FD, will become equal to the weight of this oil droplet. When this happens, this oil droplet will then stop accelerating, stop accelerating, and it will flow, or it will fall down at a constant velocity. What is this velocity called? The forces become balanced and the velocity becomes
Terminal
constant.
velocity.
Yep, it's called terminal velocity. So this fluid, this oil droplet will fall down at terminal velocity. And that is the velocity with which it will hit the bottom of this tub. So these are the forces that you need to know. Now, upthrust has a formula that we just discussed. It's rho v G, which in this case the V represents the volume of this oil droplet. Rho represents the density of the fluid in which it is falling. G is the gravitational field strength. And if you talk about the viscous drag force, so in order to calculate the viscous drag force, you need Stokes' law. There's a law called Stokes' law. It can be used to calculate the viscous drag force. Okay, so Stokes' law is equal to viscous drag force is equals to 6 pi, I call this n, but this is not n, okay, and rv. Okay, now let me explain each and every term in this equation. The n, this is actually the coefficient of viscosity, or what else is it called?
I'm not sure, but index of viscosity, viscosity index.
Index of viscosity is written in the book, right?
I don't know. I'm not sure.
Well, okay,
Wait,
if
I'll
you're
check.
not sure, I have not heard about the index of viscosity, but I did hear about the coefficient of viscosity. So coefficient of viscosity. And this is actually fixed for each fluid. This is constant for every fluid. By the way, the more viscous a fluid is, the higher will be the value for N, okay? Remember that. The more viscous a fluid is, the greater the value for N. It represents the coefficient of viscosity. Then R, what does R represent? R represents the radius of the oil droplet, the radius of the circular or the spherical object which is falling. Radius of oil droplet.
It's just coefficient of viscosity.
Okay, it's coefficient of viscosity. And then this V represents, what does the V represent? Any idea?
Velocity
Which velocity?
of the object. Terminal velocity.
Terminal velocity of that object that it represents. Okay. And now remember one thing, for this Stokes law to be applicable, the motion of this object should be non-turbulent. Non-turbulent, meaning it should be flowing, the fluid should be steady. There shouldn't be wave currents in the fluid. Do you know what turbulence is?
Yep.
What is it? Okay, it has eddies. So non-turbulent means that its flow should be laminar
Smooth. Yes.
or smooth. Okay, it should be slow moving object. Oil droplet will fall down slowly. Okay, if the object is flowing down at a very high speed, then Stokes law will not be applicable. And when the object is moving at very high speed, then the viscosity, the force of viscosity also becomes very, very small, or the viscous drag becomes small. But it's the upthrust force that keeps on increasing actually. But before this, let me tell you that the upthrust force is actually applicable on fast moving objects. If the object is not moving slowly, if it's moving fast, then the Stokes law will not be applicable. Uh, if it is not moving in a laminar fashion, then to Stokes law will not be applicable. So, and I told you that the N represents the coefficient of viscosity, and it depends upon fluid to fluid. If a fluid changes, then this value changes. But as long as the fluid is the same, this value will stay constant no matter what the quantity of fluid is. Then after
Okay.
this, also the viscosity is also dependent on temperature. So any idea what's the relationship? Think about hydrogen bonding. What did I just say a
Oh,
few
right,
minutes ago?
right. The hydrogen. Right, right. There's if enough heat is supplied to break the hydrogen bonds,
Okay, then
so they can break
this is in
down.
terms of water. Okay, this is in terms of water. If you do hydrogen bonding, sorry, if you provide heat to the water, the hydrogen bonds will start breaking, and if they start breaking, viscosity will decrease because viscosity is high because of the high hydrogen bonds, right? So this
Yep.
viscosity is actually temperature dependent. This coefficient of viscosity also changes with temperature. Okay, if remember, if the viscosity changes, then that means the coefficient of viscosity will also change. If the coefficient of viscosity changes, then that means that either you've changed the fluid or you've changed its temperature. Okay, either of these two possibilities will be there. Okay, so this was a very small portion of Stokes law in your syllabus. And after this, we start out something else. It's called, yeah, Hooke's law. Okay, after this is falling method, viscosity of a liquid, core practical. Okay, so I cannot make you do the practical over here. By the way, physics practicals usually are very, very easy. Um, Hooke's law, force and extension. So the force applied on a spring, and this is the extension of that particular spring. Okay, if this is the Hooke's law, and I were to ask you to draw out a graph of force against extension of a spring, and how will the graph will look like? It's going to be a straight line passing through the origin until a particular point after which the graph will start curving. This is extension, this is the force axis. This point after which the graph starts curving is called the limit of proportionality of that spring.
Proportionality.
Limit of proportionality.
Force proportional to extension up to a point.
Yes. And now, just after this point, there is another point called the elastic limit.
Or the team's tensile strength.
Tensile strength? What? What to do with the tensile strength over here? I don't get your point. Tensile strength is dealt when you're dealing with wires. Hello?
Yes, yes.
Oh, were you asking something about the tensile strength?
Yep.
Tensile strength
No,
is based.
I was asking whether this was tensile strength.
This is the tensile
That's fine.
force. Yes, this is the tensile force. It can be tensile force or it can be compressive force as well. Okay? Tensile
Okay.
means that force which leads to an increase in length, and compressive means that force which decreases the length. Now, this is called an elastic limit, and this is the point till which, if if the deforming forces are removed, before this point, deforming forces are removed. Before this point, the spring will regain its original shape. Okay, so even slightly beyond the limit of proportionality, the spring is extended, but then immediately the force is removed. Spring will return back to origin. The extension will return back to origin. And keep in mind this on the x-axis is the extension, it's not the length, okay? It's not the total length of the spring, it's just the increase in length, the extension of the spring. If this was the original spring, now after addition of the force, its length increases. So this difference in the length, this one is extension, okay? This was the original length, and this is the final length. So what is extension? It is the difference in these two lengths. You get Hooke's law and this graph.
Yep.
Now the area under this graph represents the energy stored inside the spring. Okay, it is the elastic potential energy stored inside the spring. Now if the graph is extended beyond the elastic limit and then the force is removed, the spring will undergo elastic deformation. Elastic deformation means that it will become permanently extended or permanently deformed. Deformation, I hope you know what deformation means. It means a change in shape
Yep.
of an object, which is due to the force applied on it. So if a spring is hyperextended, then if the force is removed, it will return back not to the original length, but rather it will have a length which will be greater than the original length. If this was the original length, this length would become permanently increased if it is extended beyond the elastic limit. And if the spring is extended beyond the elastic limit, then the force also change, the graph also changes. So basically the force against extension graph will look something like this. This is the force, this is the extension. The graph would first increase, then it would curve. Okay, let's say the elastic limit was somewhere over here and this was the limit of proportionality. We've extended it beyond the elastic limit. Now when the force is removed, this spring will extension will not return back to zero, but rather will return over here, meaning this part would be the permanent extension or the permanent deformation or the plastic deformation. And this is only possible when the spring is extended beyond the elastic limit. This is the elastic limit, this is the limit of proportionality, and this, okay, the upward graph, this is called the loading graph, and the downward graph, it's called the unloading graph. Okay, unloading. And the area which is in between these two graphs, this one, this is actually representing the heat energy which is wasted, due to which this graph, this spring became permanently deformed. And the area, this total area, the total area, this represents the area, the work which is done on the spring, or done, the total work done on the spring. And the area in between these two graphs, this one represents the heat energy which got wasted. And this heat energy causes the spring to heat up. It causes the spring's temperature to rise as well. How to calculate the energy stored inside a spring within the limit of proportionality. This is your spring. Force within extension is the graph that you've drawn. You need to calculate the energy stored inside the spring. I told you that the energy stored in the spring is the area under this graph. So if you calculate the area of this graph, it's going to be half times the height, which is of f, multiplied by the base of this triangle. Half of x is the area, which is actually the energy or the work done on the spring, or work which is stored in the form of elastic potential energy. Now, if I were to tell you that force is actually proportional to extension according to Bohr, and F is equal to kx, and if I plug this at kx instead of F over here, what will I get? I will get half times, instead of F, I'll replace the kx, instead of x, I'll place the x, and I'll get half kx squared. This is also a formula for calculation of energy stored inside the spring, half kx squared, where k represents the spring constant and x represents extension. Okay, half k x squared is also the energy stored inside the spring. These are the two formulas that you must know for the energy stored inside the spring. If you need to calculate the change in energy between 2 points, you calculate the difference.
Okay.
This is x1 and this is x2, and you want to calculate this area. How are you going to do that? Well, this is, if you look at it carefully, this is actually a trapezium. You can apply the formula for trapezium, or what you could do is you could calculate first the total energy till the x2 and then subtract the energy till the x1 from it. Meaning you can do this: half k x2 squared minus half k x1 squared, which will give you the change in energy from x1 to x2. Did you get what I just did till here? So the quick recap of your O levels. Not this part, but like the previous one, the F is equal to kx1.
Yeah.
What is elastic limit?